everyone, in this video I'm happy to present my final project titled Neural-like Vector Symbolic Architectures for Behavior-Based Robotic Navigation, Bypassing Symbolic Computations. To set the context, let's consider the fundamental challenge in robotics. How do robots perceive the environment and then act upon it? At the heart of this interaction lie two essential components. First, sensors. They are devices translating environmental changes into signals. And second, actuators. Think of motor driving wheels or robotic arms. These are the mechanisms that allow robots to act upon the received signals. Traditionally, robotics has leaned heavily on symbolic computations, especially in represented environments. A common method involves using graph theory, where environments are portrayed as graphs. To illustrate, the graph on the right shows path planning. Here, nodes represent locations while edges symbolize paths between them. Now, let's visualize the scenario. Consider a robot in a car escape task. It must exit an enclosed space, locate a light source, and stay within the illuminated area while evading obstacles. Simple for humans, perhaps, but for robots, this demands a series of intricate decisions based on sensory input. So a prevalent approach to this challenge has been the behavior-based control using symbolic computations. Here, robots segment their actions into behaviors like advance, dodge, or pursue light, guided by the data from their sensors. The strategy is represented on the right in a pseudocode format. However, a significant limitation lies in its reliance on symbolic relationships, which often prescribe how a robot should respond to its sensory inputs. So building on the limitations of the existing methods, I propose an innovative alternative, vector symbolic architectures, or VSAs. VSAs use high-dimensional hypervectors for symbolic encoding but without traditional symbols, aiming for a more direct mapping between sensors and actuators. In fact, our VSA approach is rooted in a broader concept called hyperdimensional computing. This paradigm operates in vast dimensional spaces, bringing powerful computational abilities and a high tolerance to noise, which is crucial for real-world scenarios where sensors might not always give perfect readings. So, where does this fit into our robot task? Instead of hard-coding behaviors, we'll train our robot using a dataset comprising sensor readings paired with appropriate actions. By learning from this dataset, our robot will create a program hypervector, which captures the essence of all its training. So let's now delve into the core of our robotic solution. If you take a look at the figure, it showcases our proposed framework. So during the training phase, we use robots' data to train the VSA. The training data consists of sensor readings matched with corresponding actions. These pairs are derived from the behavior-based algorithm shown in the previous slide on the right. And this will ensure the data is both adaptable and easy to gather. So each of our robot sensors and actuators has a unique label or hypervector. Sensors capture the environment's detail, which are then translated into language the robot understands, leading to the creation of condition HV and the result HV. Think of these as the robot's current situation and its planned action. All this information is compacted into a master guide called Prog HV, which directs the robot's learned behaviors. Next, in the query phase, the robot refers to its past training to see if it recognizes its current situation. If it's a new scenario, the robot adapts and learns. An essential tool here is a cleanup memory, which ensures the robot's reactions remain sharp and accurate. The cleanup process can be represented as result HV is set to VSA cleanup of condition HV tensor prog HV. So in simpler terms, it's a robot's way of refining its actions based on both its past training and current scenario. So now, what should we expect from this project? We've planned a series of experiments to measure the effectiveness of our VSA models. Firstly, we'll evaluate how well our model can learn from the training data. Given the strengths of hyperdimensional computing, we anticipate robust learning with minimal data loss. And second, in real-world setting, a robot might face situations it hasn't been explicitly trained for. So we'll also test our model's adaptability to these novel scenarios. Because of the VSA's high-dimensional nature, we expect it to handle unexpected conditions reasonably well. And another focus is to assess how tolerant our model is to noise and its proficiency in retrieving accurate output, especially with the aid of the cleanup memory. Finally, we'll benchmark our VSA model against traditional behavior-based controls. The goal is to determine if our approach can offer a more efficient, faster, and accurate solution in robotic tasks. So in summary, we're on the brink of what could be a novel approach in robotic computation and making robots probably more adaptable and effective in diverse settings. Thank you very much.